Thank you for watching the presentation of our work, Real-World Assignments at Scale, to reinforce the importance of algorithms and complexity. I am Eric Soul from UNC Charlotte. This is a joint work with students at UNC Charlotte and my colleague Kapati Subramanian, and also Jamie Payton from Temple University. This work aims at addressing the discrepancy in belief between instructors and students regarding algorithm courses. On the one hand, instructors tend to believe that algorithm courses are critical to CS students' theoretical foundation. On the other hand, students tend to believe that algorithm courses are overly theoretical and that calculating complexity and proving correctness are not applicable to real-life problems. They believe they will study obscure paradigms that are unimportant to real-life problems. As a result, students tend to be not as engaged as they should be, and failure rate in those courses tend to be high. The algorithm course in many universities has become a weed-out class. In this work, we present the Bridges framework, which improves the education of CS students by increasing their engagement. The main strategy of Bridges for algorithm courses is to bring real-world dataset into the classroom that can scale to sizes where complexity matters. Out of these datasets, we have designed assignments for students to solve algorithmic problems that feel real. On top of that, Bridges is going to provide visualizations of student-generated data structures. What Bridges provides are essentially interesting input and output features for student assignments. For instance, Bridges provides song lyrics data through Genius and road-level data through OpenStreetMap. Once the students have solved the problem, they will be able to generate visualizations of their work through Bridges visualization types such as trees, graphs, or images. The client to the Bridges framework are available in Python, C++, and Java. We surveyed algorithm courses throughout the country. We found that most courses tend to follow the same structure. They usually start by talking about order of growth and the big O notation, and follow up with proving correctness and computing complexities. Then they usually discuss advanced data structures such as trees, graphs, and hash tables. The class tend to follow on with algorithm design techniques such as divide and conquer and dynamic programming. What we are proposing is a set of engaging assignments that will map to most of the algorithm curriculum. These assignments are going to deploy multiple engagement strategies such as enabling students to visualize the output of their work or working on real-life data or real-life problems. These assignments tend to leave students with some choices as to the problem they solve, and they are designed to map to areas that are of common interest of students. The first assignment is plotting complexity. It is a useful preliminary that many courses tend to already do. In this assignment, students are going to compute the runtime of different complexity functions, assuming they're running on different machines. Students can pick specifications of their own machine or of classic systems that they may have used in the past. For instance, they could pick the specification of their favorite gaming system. Bridges is going to provide visualizations of the computed runtimes. Students will be able to see that a better complexity often trumps a faster machine. The next assignment is a sorting implementation assignment, which is a classic assignment given in algorithm courses. Students are going to implement different sorting algorithms and compare their runtime. Bridges is going to provide visualizations of the data structures used during sorting. Bridges also provide real data to sort. One could use title of books or the magnitude of recent earthquakes. Bridges also supports the automatic benchmarking of sorting algorithms and displays the results as a line chart. Another assignment is the book distance assignment. Students are going to compute word frequency vectors of classic text using a dictionary data structure. Then, the similarity between two books can be estimated using the Euclidean distance between those frequency vectors. One could go one step further and compute clusters of books using islanding graph techniques. Bridges does provide access to a large number of text to use in this assignment. Bridges can also help in visualizing the dictionary data structure and by visualizing the islanding graph. Mountain Pass is an optimization assignment derived from the classic Nifty assignment published a few years ago. You are given the landscape of a mountain as an elevation map, and you have to travel from the left side of the mountain to the right side of the mountain. In the classic greedy variant, one always goes right and picks the pixel that minimizes the difference of elevation. Finding the best path that always goes right and minimize the sum of squared elevation difference is a typical dynamic programming exercise. Finally, if one allows to go from one pixel to any of the neighboring pixels, then the problem becomes a classic shortest path problem. Bridges provide elevation data for any latitude-longitude bounding box on Earth. This allows students to choose where on Earth they are going to solve the mountain path problem. One can visualize the landscape as an image and see the path taken through the mountain. Routing in a city is a shortest path assignment. Bridges enables you to access the road network of any place in the US. You can request the city you live in, you can request the city you were born, you can request any latitude-longitude bounding box in the United States. When students have the network of a place in the United States, they can apply classic shortest path algorithms such as Ford-Bellman or Dijkstra's. Bridges enables you to visualize the map that you have fetched, but also to visualize the shortest path computed by your algorithm. Shortest path algorithms can also be benchmarked automatically by Bridges by passing larger and larger maps to them. Hollywood analysis is a graph assignment where students will have to perform BFS in a bipartite graph. The assignment is rooted in the Bacon number game, which is defined as follows. An actor has a Bacon number of 1 if he or she was in a movie with Kevin Bacon. An actor has a Bacon number of I plus 1 if they were in a movie with someone with a Bacon number of I. Computing the Bacon number of an actor boils down to computing the BFS distance to Kevin Bacon in an actor-movie graph. Bridges provides a toy movie actor dataset that is good for debugging. Yet, a larger dataset is available that encompasses all movies since the 1910s. The graph visualization of Bridges enables you to see the BFS path between any actor and Kevin Bacon. To summarize, we showed a sequence of engaging assignments that can be used to teach an algorithm course. The assignments cover the curriculum of most algorithm courses. Bridges enables assignments to feel real by providing interesting datasets and visualizations. While we did not present student feedback, it is available in the main paper. The Bridges project is currently looking for adopters. The framework has been deployed across many US universities and has impacted over 1,000 students. Adopters will receive technical support from the Bridges team and a stipend. If you wish to adopt Bridges in your course, contact us at any of these email addresses.